Hello class, how are you doing? We're going to continue our video with doing some examples regarding Lagrange multiplier. And Lagrange multiplier help us to optimize objective function. Objective function could be the cost, it could be the revenue, it could be profit, it could be relationship between quantities. You either make the relationship better or worse. You can talk about objective function could be sales of different quantities. How many of each of these are sales that it maximize my sales, and if the sales is maximized, I'm going to get more commission. And what Lagrange did, if you remember on the last video, an example that we purchased a property and the property was elliptical shape. And you are asked to build a house in this one. The house must become rectangular shape, the foundation, and it must have the largest area inside that elliptical shape. You cannot make a rectangle like those. Therefore, the best rectangle with the largest one was right here. Therefore, we didn't know how much of it is for that the x value has, because this is your that's your a squared is 16, a is plus minus a 4. How much of it is going to belong to this x, and how much of the 3 belong to that x. Therefore, this distance must be whatever it is, less than 4 and greater than 0, and that distance right here must be less than 3 and greater than 0. And if you remember, we said the objective was we want to find the area here, and that area is x times y, but because we have 4 of this rectangle, we write 4xy, and that was your objective function, your area as a function of x and y. Because we've been dealing with x and y and a z, I'm going to call the area a z function of x and a y, and that becomes 4xy. And whenever we ask to graph the 3-dimension, sometimes it would be easier if we do the level curve. Means they call it the topographic. Look at the surface from the top. From the top, at the different level, you see a different curve. Look at the mountain. At the point, you see a point, then you see a curve, like an elliptical one, then you see another one, and you see the ellipse get bigger and bigger and bigger as you go down. Therefore, the level curve of a 3-dimension is always become a 2-dimension. Therefore, if I call this one a c for xy, your y equal to 4 over c over 4x. What happens if c becomes 0? You have a point. Therefore, this one, what you see at the bottom, you see a point. But gradually as you go up, your z become 1, means your c become 1. Your graph is going to be a rotated hyperbola. If 2, the hyperbola moved a little bit up. If 3, it go higher. And your constraint was an ellipse. And I promise you, at some point, your objective function and the constraint meet at a point right here. And we did say by having 2 objective function, that's the function of x and y, but that's not a function of x and y, that's a relationship. You have to write it in explicit form by having the z involved and taking the 1 to this side and put the z on the other side. This is called constraint. And we know the gradient is always normal to the level curve. We talk about this one extensively, about level curve. Therefore, this gradient is going to become normal, and the gradient of that one is going to be at the point of a tangency normal to this objective function. And the gradient of the that was the gradient of the constraint. The gradient of a constraint is that elliptical, and its gradient is going to be normal. The gradient of the objective function is also normal to that red one. Therefore, the two gradient is going to be parallel with each other. Because they are parallel, it could be on top of each other, it could be on the same direction. All I know, they are parallel with each other. Because they are parallel with each other, they are constant multiples of each other. And the person invented this one and wrote them in a paper. It was Joseph Lagrange, and he said the gradient of the objective function is the constant multiples of the gradient of the constraint. We talked about this in previous video, and today I'm going to ask you a favor. And I forgot to say something else in here. Remember, in here, the level curve has two branches, a branch here, a branch here. And sometimes you're going to have two ordered pair. And what do you know about these two ordered pair? And this time is the area. Area, you always have to be positive. Therefore, either have to be both negative or both positive to give you a positive. Therefore, maybe another ordered pair they give you here. Therefore, if they give you more than one ordered pair, when you solve the system, you have to plug both of them into the objective function and see which one give you the highest value, which one give you a minimum value. In here, I'm going to ask you to minimize. When I said minimized, I'm asking for the minimum value. That could be a cost maybe. And that's my objective function. Give me a x value and a y value that give me the minimum z. Somebody said 0 and 0. Your z is 0. Because for any other number, x and y, when you square it, become positive number, your z is greater than 1. Therefore, the minimum value here is 0 and 0. But they're going to say, no, I don't want the minimum value of the function. I want the minimum of this one under a specific constraint. And my constraint is this. I need the minimum z value under this constraint. Therefore, maybe the minimum is not 0. Maybe it's something else. But because this is a function, I know it does have a gradient, and that's my objective function. I know this one is a relationship between x and y. It's not a function of multivariable, it's a function of single variable if I solve for y. But I gotta make it function of multivariable to have the gradient have same component at that gradient. Therefore, I'm going to call this one my constraint, only the g, moving x and y to one side and z to the other side. I'm going to put my z in here. Therefore, the constraint is x plus 2y minus a 5. Right now, my gradient has the same number of the component as my objective function. And in order to use Lagrange, the constraint and the objective function, the level curve must meet at specific point which their two gradient become constant multiples of each other. Therefore, if they are not constant multiples of each other, you're not going to have no solution. But let me see if these are and have a solution. The gradient of the function must be equal to the constant multiples of the gradient of the constraint. This is 2x, comma 2y equal to lambda 1 and 2. Therefore, here your lambda is 2x. And in this one, the 2 lambda is, let me make sure I did it right. The gradient of that one is 1. The gradient of that one is 2. There is nothing wrong with it. 2x equal to that one. And this one is that one. And 2 lambda is equal to a 2. Oh, here I have 2y equal to 2 lambda. Here means lambda equal to y. In this relationship, lambda is y. In this relationship, lambda is 2x. I'm talking about that relationship and this relationship. But this one is 2 equation, but I have 3 variables. Remember, whenever I give you a constraint, that constraint is also a relationship between x and a y. Don't make mistake. That's not a relationship between x and a y. That's a relationship between x, y, and a z. That's your objective function. You're trying to minimize it. Do not use that one. You have to use your constraint because it's already, that relationship is already given. Therefore, if x plus 2y minus a 5 is 0, I have three equations. 1, 2, 3, three variables. Somebody said, I don't have a lambda here. Yes, you can add a lambda by 0 times lambda. Then, what is your x? Lambda over 2. What is your y? Lambda equal to 5. 2 lambda plus half a lambda is 5 half lambda equal to 5 over 1. I'm going to flip that both sides, or I'm going to multiply both sides by 2/5. That's what I mean, multiply by the reciprocal. This lambda is equal to 2. If lambda is 2, x is 4. If lambda is 2, y is 2. Therefore, x has to be 4 and y has to be 2. I don't know if I did it right. I'm going to go in here and I'm going to check my work. And I want to make sure my work, these x and y satisfy. What is my x? 4. What is my here? 2 times 2 is 4. 8 minus 5. I did something wrong. You got to make sure you check your work and make sure your work is right. Here I said 2x is equal to what? Lambda. Therefore, 2x is equal to 1 lambda. And what was your lambda? Your lambda is a 2. I don't know how I came up with x equal to 4. If lambda is 2, therefore your x is 1. If lambda is 2, 4 over 2 is 2. I made that mistake purposely to let you know, don't ever go forward. Always check your work before it's too late. Therefore, I got 1 and 2. Let me see if it works. 1 plus 2 times 2 is 4. 1 and 4 is 5. 5 minus 5 is 0. It works. Therefore, 1 and 2 produce the minimum value. Under this constraint, what is that minimum value for 1 and a 2? For 1 and a 2, the minimum value is 1 plus a 4 and is a 5. Did you see I said when it's a function by itself, the minimum value was 0 at 0, 0. But in here, under that constraint, when you draw that plane, 1 and 2 produce the minimum value. Therefore, if you are a salesperson, or if you are a producer, and make the first object by the cost of first item $1, and the cost of a second one 2, you will minimize the cost. Other than that, the cost will gonna be either higher or lower. Let's do another problem. Another problem I'm gonna do, I'm gonna make it a little bit more difficult at the first one, because sometimes maybe you have more than one order paired. Therefore, let me think. Something it has a maximum and minimum both. I'm going to write f of xy, same example I did, x squared plus y squared. I'm going to add something else to it, 3xy. I'm going to go right here. I'm going to say my constraint is x squared plus y squared. I can make my constraint to become a circle. But sometimes I'm going to say less than or equal to 1. What does it mean? It means my constraint is a unit circle. Any order paired inside here and any order paired on the boundaries are your solution. Okay, that's not hard. That's your objective function. I'm going to write my constraint, but I cannot write my constraint as a function of z, because that's an inequality. And Lagrange, you cannot apply Lagrange multiplier here. Lagrange multiplier, your x squared plus y squared must become an equal, not an inequality. Oh, how about if I, for finding the numbers or the pairs on the boundary, I use Lagrange. I got it. And for the one inside, I use the other method we learned that take the partial derivative respect to x and partial derivative respect to y and simultaneously make it equal to 0. Therefore, I have to break that problem to two problems. One part of it can be done by Lagrange. Then in this one, I can write as a function of what? Z. F of xy equal to x squared plus y squared minus a 1. This is my constraint because I already have a F. I'm going to call it G. I have a Freddy. I'm missing a Ginger. What is the gradient of the Ginger? It's 2x and a 2y. What is the gradient of the Freddy? Oh, Freddy is complicated. It's 2x plus 3y. And this is 2y plus a 3x. Then this gradient have to become constant multiples of each other. Therefore, 2x plus 3y must become equal to lambda times 2x. That's one equation. Another one, 2y plus 3x must become equal to lambda times 2y. But this is three variables, two equations. I have to have my constraint. I got it. Let me go back in here because I have only lambda here and the rest is x and y are mixed. Let me solve for lambda here and say my lambda is 2x plus 3y over a 2x. And let me solve for lambda here and say 2y plus 3x equal to 2y. Therefore, when you have two quantities equal to the same amount, these two quantities must become equal to each other. Then what do I have? I have 2x plus 3y over a 2x equal to 2y plus a 3x over a 2y. Would you cross multiply these or multiply both sides by 2xy? That become 4xy plus 6y squared equal to 4xy plus 6x squared. Bingo! X squared equal to y squared. I got it. From these two equations, I find that x squared is equal to y squared. Therefore, in the constraint, x squared is equal to y squared. I either replace x squared with y squared or y squared with x squared. Therefore, I'm going to write x squared plus x squared equal to 1. 2x squared is 1. X squared is 1/2. Then x has two values, plus minus radical 2. Your y also have two values because they are the same. Therefore, your x could be radical 2 over 2. Your y could be radical 2 over 2. Your x could be plus radical 2 over 2. Your y could be negative. Your x could be negative radical 2 over 2. Your y could be positive. Your x could be negative radical 2 over 2. And your y should be negative. You have 4 different combinations. You have to do all 4 of them. But when I do all 4 of them, what was my x squared? My square is 1/2. What is my y squared? My y squared is 1/2. What is 1/2 plus 1/2? And it doesn't matter which one you get. When you square it, you get a positive number. Therefore, let's try to do one at a time for you to see it. Okay. If I square radical 2 over 2, you get 2 over 4 plus 2 over 4 plus 3. When I multiply this one, it becomes 2 over 4. This is 4, 4, 4, same denominator. 2 plus 2 plus a 2, no, plus a 6. 10 over 4 is 5/2. Okay. For that one, you have 5/2. That's your z value. Let me do my z value here. You have 2/4 plus 2/4. But because this is negative, that become plus 3 times negative 2/4. Because that's become 2 times 2, radical 2 times radical 2 is 2, 2/4, but positive times negative is a negative. And then you have 2 plus 2 minus a 6 over a 4, and that becomes negative 2/4, which is negative 1/2. When I plus these two in there, negative times negative is a positive, and you square each of them become positive. For this one, you also have 5/2. And for this one, your z is going to become 1/2. Therefore, here you have 5/2 and you have negative 1/2. Okay. Therefore, these 2 points gonna give you maximum, minimum, but I only try on the border. I have not done inside. Inside, I have to go back right here and say, what is the partial derivative respect to x? Is 2x plus 3y. You gotta set it equal to 0 simultaneously with y. Then the only way I can make this one a 0 if your x become exactly negative 3y over a 2. And when your x is negative 3y over a 2, no, I'm sorry, your y is, what am I doing? Your x is negative 3y over a 2. You have a 2y here, negative 9y/2 here. Whatever you do right here, your y is going to be 0. If your y is 0, your x is 0. You have another order pair. Okay, put the order pair right here. Your z is 0. Then right now, you have 3 values. That's your maximum. That's your minimum. Somebody say, what is this? Let me test it. What is this? I need partial derivative respect to xx. Respect to xx is 2. See, xx is positive. It might be a minimum value. I don't know. It depends to the d. Your f of xy is 3. F of y is 2. Your determinant is 2, 2, 3, and a 3. Oh, the determinant of a d is negative. If the determinant is negative, it's a saddle point. Therefore, yes, 0, 0 is a saddle. Radical 2 over 2 and radical 2 over 2, if both become positive or both negative, that gives you 5/2, and that's the max. And if you have radical 2 over 2 minus radical 2 over 2, or negative radical 2 over 2, radical 2 over 2, these two g value is negative 1/2, that's your minimum. Therefore, you have a max, you have a mean. These are relative max because you have too many turning points, and you have a saddle point. These are some application of Lagrange multiplier. I hope you enjoyed it. I hope the video did not go too long. Thank you for watching.